Today, we're going to continue looking at parameterized curves. And we're going to go back to this circle to help us practice making some adjustments to our circle so that we can learn a little bit more about how parameterizing a curve will work. So if you would recall, if x is cosine of t and y is sine of t for t between 0 and 2 pi, this will trace out a circle of radius 1 with its center at the origin. The parameterization part gives us a starting and an ending point, starting at 1, 0 and going once around counterclockwise. So that's starting at 1, 0 when t equals 0 and ending at 1, 0 when t is equal to 2 pi. What we want to visualize are the x and the y coordinates separately. We want to think about what the x is doing and what the y is doing. We want to do yesterday's problem where I gave you the graphs of x of t and y of t and produced the parameterized curve. Now we want to take the parameterized curve and look at the graphs of x of t and y of t and see how they compare. And as usual, we want to start with something familiar. So if we just look at x equals cosine of t, let's draw a picture of x equals cosine of t. So I've got I'm going to have x on the vertical and t on the horizontal. The cosine graph starts off at 1, drops down to -1, and then comes back up to 1. I don't know why I made it so squished. I think in my mind, originally I was going to draw them next to each other. Then I realized there wasn't going to be enough space. And rather than just changing halfway through, it took too long for the instructions to reach the pen. So let's take a look at the graph of cosine. Cosine starts off at 1, drops down to 0, then drops down to -1, back up to 0, and then back up to 1. So here's what the graph of cosine looks like. And this is what the x coordinates are doing in our graph. The x coordinates are starting off at 1, dropping down to -1, and then coming back up to 1. The x coordinate starts off at 1, hits 0 at pi over 2, -1 at pi, 0 again at 3 pi over 2, and back up to 1 at 2 pi. So when we see this graph of cosine going down and then back up, that we're watching the x coordinates go down and then come back up. If we look at the y coordinate, we look at the y coordinate, the y coordinate is going to be tracing out a sine graph. So the y coordinate starts off at 0, goes up to 1, back down to 0, down to 1, down to -1, and then back up to 0. So if we just imagine the y coordinate, when we go around the circle, we start off at 0 when t is equal to 0. We go up to 1 at t equals 2 pi, down to 0 at t equals pi, down to -1 when t is equal to 3 pi over 2, and back up to 0 when t is equal to 2 pi. So that's what it looks like going once around. So the y coordinate goes up and then down and then up again. And the x coordinate went down and then back up. So we want to see this motion broken down into pieces, just like if we had an Etch-a-Sketch. So if Here, one of the knobs on the Etch-a-Sketch controls the horizontal, and the other knob controls the vertical. The horizontal knob spins to the left and then spins back to the right. The vertical knob spins up and then down and then up again. And that's how we make a circle on Etch-a-Sketch.
Professor Rich, can you please show the Y vertical shift on the graph again? Can you show that again, please?
I'm not sure what you're asking about.
You see how the X, I'm sorry, see how the cosine, they go counterclockwise and then they go one circle. How the, the, the sine go? Can you show us again?
So it's the cosine and the sine that are making the circle in the coordinates X and Y. So if we look at what happens when t is equal to 0, the X coordinate is equal to 1. And then as t goes from 0 to 2 pi, we see the X coordinate start off at 1, go to 0 to -1, back up to 0, and then back up to 1. So that's going here, the X coordinate is moving to the left, and then the X coordinate moves back to the right. So the X coordinate goes from 1 down to 0, and then back up to 1. If we trace the Y coordinate around with the sine of t, Y coordinate starts off at 0, goes up to 1, down to -1, and then back up to 1.
Oh, I got it. I see it.
So if we put those two motions together, in this first quadrant, X is decreasing while Y is increasing. And then in the second quadrant, X is still decreasing while Y is decreasing too. In the third quadrant, X is increasing, but Y is still decreasing. And in the fourth quadrant, they're both increasing again. So we ended up with this circle going once around counterclockwise, starting at the point 1, 0.
Thanks.
So we want to be able to change aspects of this circle. Specifically, we want to be able to change the radius and the center. And we also might want to start at a different point. And we also might want to go around the other direction. So if we think about starting off at 1, 0, let's just change one thing. I'm going to trade my sine of t for a negative sine of t. So let's do as a second example. I'm going to keep cosine of t as my x coordinate, but I'm going to trade my y coordinate for negative sine of t. And I'm still going to go for t between 0 and 2 pi. So up here, I have x is cosine of t, and this blue graph, we have y equals sine of t. So now I want to to change my sine of t for a negative sine of t. That's going to change what happens in the y coordinate. So now my y coordinate is not going to be governed by up, down, then up again. Now my y coordinate will be the other direction. So now my y coordinate, instead of going up, down, and then up again, will still start off at 0, but it'll go down and then up and then down again. So here, y is now negative sine of t. So when we're still going to get a circle. but where before my x went from 1 to -1 back up to 1, instead of y going up, down, and then up again, y is going to go down, up, and then down again. So instead of y going up, down, up again, y is going to go down, up, down again. We're still going to get the same graph. We're still going to be looking at a circle. Kind of messed up my color coding, but sorry. Our circle is still going to be centered at the origin. When t is equal to 0, cosine of 0 is 1, and negative sine of 0 is still 0. So we still start at the point 1, 0. That'll still happen when t is equal to 0 and when t is equal to 2 pi. In the x direction, we still start off at 1, go down, and then back up again. But in the y direction, we've changed the direction. Y is going to start off at 0, go down, and then up, and then down again. So as x goes down and up, y goes down, up, and then down again. So we're going in the opposite direction. So now we still have a circle, still have a radius of 1, still centered at the origin, still starting at 1, 0, but now going once around counterclockwise. Sorry, clockwise. Still a circle, still radius 1, still center at the origin, still starting at 1, 0, but now we're going once around clockwise.
Professor Rich, could I have a quick question? On the right, you have the note 1, 0, and t equals 0, t equals 2 pi. What does that mean? Could you show me?
So this is the point where it starts. When t is equal to 0, cosine of 0 is equal to 1, and sine of 0, minus sine of 0 is equal to 0. The 1 is giving us the y coordinates. 0 is the x coordinate. Sorry, I said that backwards. Cosine is the x coordinate and the 0 is the y coordinate. Because cosine is the x coordinate and sine, or negative sine, is the y coordinate.
And what if the t equals 0 and t equals 2 pi?
That's the parameter, and those are all the values of t that we're plugging in.
Okay, thanks, Professor Rich.
So by trading our sign for a negative sign, we've sent the graph in the other direction. We maintained our same starting point, but we reversed the direction of the curve. When we parameterize curves, we get a direction, a starting point and an ending point, and a direction that the curve is going. Let's take a look at making some other changes. If you would recall, when we talk about graphs, we know that multiplication will produce a stretch. As far in terms of transformations of graphs, multiplication produces a stretch and addition produces a shift. We could also, if we stretch by something less than 1, then we'll get a shrink. So multiplication will stretch or shrink, and addition will shift. So multiplication will stretch and addition will shift. So if I want to move my circle around and change its radius, I'm going to still keep my cosine of t as the core, and I'm going to keep sine of t. I'm going to go back to just sine of t, and this is going to still be for t between 0 and 2 pi. These are all the values of t that we're going to be plugging in to our 2 coordinates. If I want to change the radius of my circle, I can multiply the cosine and the sine, because that will stretch the circle out to a bigger circle. Or if I multiply by something less than 1, I will shrink the circle. But that will be controlled by multiplication. The radius will be controlled by multiplication. I'm going to use different coordinates because, or sorry, different constants, because I can take my circle and stretch it into an ellipse by using different coefficients. So multiplication by a in cosine and b in sine will stretch or shrink the radius. That's what multiplication does. It stretches or shrinks the radius. Addition will shift. So if I add if I use addition, I can move my center to some other location, because addition will shift the graph. So now, if a is equal to b, then we'll have a circle. With radius a or b, because they're the same. And if a is not equal to b, then we get an ellipse. In both cases, the center is at h and k, the shift. H is our horizontal shift and k is our vertical shift. So in either case, the center is at hk. So let's take a look at a circle. And let's see what happens if we change a and b, do some multiplication. That will cause the circle to stretch. So if I multiply by, let's go with 2, and both coefficients are the same, we end up with a circle of radius 2. If instead of multiplying by the same value, let's say I multiply the cosine by 3, then what happens is we flatten our circle out, or stretch our circle out into ellipse. It's stretching more in the x direction than it is the y direction. the other thing that we want so there's multiplication producing a stretch, or I can squish it. So if instead I multiply the cosine by 0.5, that'll squish the circle in. So we still have a distance of 2 going up and down, a radius of 2 in the vertical direction, but now it's only a 0.5 in the horizontal direction. Or if I stretch it around, I can make a wide flat ellipse. But that's all being controlled by multiplication. Multiplication is in charge of the stretching and the squishing. Addition will maintain the shape and just shift things around. So if I say insert a -1 plus 3 cosine of t, that will shift the whole thing 1 unit to the left, because now the center is at -1, 0. If I move the shift down to -2 and I insert 1 plus the 2 sine of t. So now my center is going to be at -2, 1, and it will be the same shape. Any questions?
Professor, if you do, instead of the addition, if you do the negative, would it be changed? Would it be different?
As far as the addition, if we change the sign in between, remember what happened when we changed the sign of, change from positive to negative sign. So let's change from positive 2 sine t to -2 sine t. When we look at the graph, notice that the circle forms in the other direction. So when we have a plus sine t, we go counterclockwise. And when we drop this to a negative sine of t, we go counterclockwise.
Oh, so is the direction changing?
Yeah, the direction changes.
Oh, got it. Thanks, Professor.
If we go in and change the sign, let's think about this. What happens if I change my cosine to a negative? Let's see what happens. When cosine is negative, notice that we started at the opposite end. Instead of starting off at 1, 0, or sorry, in this case, 1, 1, we started off at -5, 1. We started off at the opposite end. But we went counterclockwise. If I change my sign to positive, now we start at the opposite end and go clockwise.
But the graph stay the same, isn't it, Professor Lich? They both the same graph, but the different direction. Am I right?
Yeah, we're just changing the direction and we're adjusting the start.
Thanks.
So by changing our coefficients, we can change where things starts and which direction they go. Any questions?
Professor, can I see the equation that you put in the calculator real quick? Okay, cool, thanks.
So notice that the addition, the -2 and the -2 and the +1, that determines the center. That's the shift. That's just moving that same shape around. And the 3 and the 2, in this case, a -3 and the 2, change the stretch either horizontally or vertically. I keep wanting to say radius, but it's not a radius because it's not the same all the way around.
Actually, I have a question, Professor. So usually when we plug in, let's say like -2 in a function, we shift it to the right, right? But in this case, it's shifting to the left.
Yeah, also notice how the h and k are included. It's just, we're just adding an h and we're adding a k. When when horizontal shifts go the opposite direction, that's because in the expression we're writing x minus h. So if we think about the parabola y equals a times x minus h squared plus k, the vertex is at h k. So even though it would say x minus 3 then squared, the vertex is at 3, right? Because the h is whatever we say after we say minus. So if I have, for example, let's say -1 times x plus 3 squared minus plus 4, my vertex is at -3, positive 4. But when I wrote the h up here is just h plus a times cosine of t. The h is not being subtracted, the h is just being added. But when we're looking at the vertex form of a parabola, we're writing x minus h. Because we're trying to, the h needs to be at the middle of the parabola, where that squared part is not involved. So h minus h makes 0. Any questions? This is why I don't like thinking of just do the opposite when it's h, or just do what it says when it's k. This is why formulas aren't very good. Any questions? Let's think about parameterizing a function. When we introduced the concept of parameterized curves, our motivation was to be able to describe a one-dimensional curve in R2 that could not be expressed as a function. But this needs to be backwards compatible. I can't have two separate systems where functions just can't be represented as a parameterized curve. I have to be able to parameterize everything to make parameterization the more general thing. So we can parameterize a function. So for example, let's suppose that y is equal to x squared. Since x is its own, actually, let's just write it down. We're going to write coordinates x, y, but y is equal to x squared. So I can write this as x squared, and then just say for all x. The upside down a is an abbreviation for all. So there's our parameterization. If I go into if I want to produce the graph of y equals x squared, and I want to parameterize it, I can just make x be x and y, oops, there it is, y equals x squared. Now, when I graph this, I only get this left half, or sorry, the right half. Because my parameter is only set to go from 0 to 2 pi. But if I set my parameter go from, say, -10 to 10, now I'm plugging in all the x values from -10 to 10, or excuse me, t values from -10 to 10, and now I get my whole parabola. Any questions? So it's easy to to parameterize a function. We just let x, if y is a function of x, you just let x be a function, be x, and then y can be the function of x. If x is a function of y, then we would just do the same thing. So for example, if our function says x equals y squared, that's going to be a sideways parabola. We still want to write the coordinates x comma y, but in this case, instead of saying y equals x squared, I'll say x is equal to y squared, and then just do this for all y. So if I trade my x and my y and put t squared in the x and just t in the y, I get my parabola going sideways. This is useful because if I'm stuck in function mode, I'm very limited. In function mode, I can't solve, I have to write y equals. So I'd have to try to turn this into into a function. Y is a function of x, and I would have to say the square root of x, but that only is going to get me half of the parabola. To get the other half of the parabola, I would have to put in a whole separate function, negative square root of x. So limiting. More colorful, but so limiting. But when we parameterize a curve, we don't have to worry about one coordinate being a function of the other coordinate. We write the coordinates independently as functions of some parameter. This gives us more choice and more freedom to describe more things. And so that's great. We have more ways to do something. But then again, since there's more ways to do something, that's terrible. Now we have to choose a way to do something. The further along that you go in math, the less it becomes, when you see this, do this. When you see this, do this. When you see this thing, do this thing. And you have to incorporate more of what you know to understand what's going on. And that's why math gets harder. We get kind of programmed with the ideas like, oh, well, in math class, there's only one answer. But a lot of times when we're learning math, the answer is not the point. It's not about coming up with the area of a circle. It's about how we come up with the area of a circle so we can understand the process, so we can apply the process to other things and know what situations in what situations we can apply a process and in what situations we cannot apply a process. That's what we're all about in math. We try to generalize things that we already know so we know which problems to reduce new problems to. We know how to reduce new problems into old problems. Any questions? How's everybody okay?
Not really, Professor Lich. You don't mind explain the last example for Professor Lich really quick? X equals y squared, and then the bottom we have x and y. Then on the right we have y squared comma y, and then all y. Then I see the graph you draw it's something, it's similar like something divided over something. That's why we get that track. No, that's not what it means.
No. So in the parameterized form, I want to draw this graph where y is a function of x. That's what we're limited when we want to write y as a function of x. I need two functions to draw this one parabola. X equals y squared is a parabola, it's just sideways. But if we parameterize the curve, if we switch over to parameterized, then I just replace, since I want the coordinates x comma y, but since x is equal to y squared, that means everywhere I see an x, I can replace it with a y. I see x here, sorry, I can replace it with y squared. Everywhere I see an x, I can replace it with a y squared. Here's an x, let's replace it with y squared. Then if I take it to the parameterized entry, I can put in t squared for the x and t for the y, and I get the whole parabola.
Thanks for solution. I will look further on the YouTube. Thanks for telling me the x is the y square. I see the pattern. Thanks.
Yeah.
Thank you.
So when we switch the x and y in a function, we just take the function and kind of turn it sideways. So this is a hard thing for us to get used to, because we learned from the beginning that x is always the horizontal stuff and y is always the vertical stuff. And then so for each x, we plug in a y, and then we get something like this. Y equals x squared. We get programmed with this idea. But there's no reason that the horizontal has to be the input and that vertical has to be the output. In this case, I'll take y as the input and x as the output, and I get the same shape, a parabola. It's just facing the other direction. All right. So we did a little more work with a circle. We saw how we can adjust our parameterized circle to cover different radii. We've also looked at how we can change our circle into an ellipse just by squishing it or stretching it in one or both directions. And we've talked about how to shift our circle, move the center of the circle around with addition. And it all fits into what we understand already. Adding, shifts, multiplication, stretches. Going along with operations, multiplication by 1 doesn't do anything because 1 is called our multiplicative identity. Multiplying by more than 1 will stretch, multiplying by less than 1 will shrink. In addition, 0 is in the middle. Adding 0 doesn't do anything. Adding positive shifts one way, and adding negative shifts the opposite direction. So just remember, with addition, 0 is in the middle. With multiplication, 1 is in the middle. It only seems like it's a lot to remember because it's a lot to remember. And you have to remember all of it all the time in perfect detail, and you have to remember some stuff that wasn't taught to you in the first place. Probably the most messed up thing that we do. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.
Thank you.